All right, this is physics reaction video number, I think 77, maybe 76, I can't remember. But this is an exciting one because this was a request. So he put in a request for me to watch this particular video with some particular questions about, how to get better. So I'm excited. Here we go.
Hey guys, I got my magic 8-ball right here. I'm going to do a little demonstration for you. It's all about something that Galileo figured out a few hundred years ago. What an incredibly smart man.
All right, so framing, it looks like this camera is, 15 feet away, so it's really, everything's kind of going to stay in focus. I don't think he's going to have any autofocus problems. Well, I guess it depends how far forward he walks. Yeah, it sounds good. Galileo's incline. Not 100% sure what Galileo's incline is. I should know this, but I mean, I'm just trying to think. I'm sure it's some cool way of rolling things down a hill or something. But there's some really interesting tools out here. I don't know if we're going to use all of these tools here. Yeah, and I love the 8-ball stuff. I love the decorations in the class too. These lab stations are pretty awesome, right? Because they built these shelves and they put the monitors up here. So I think that this maybe enables students to go over here and do some experimentation. So just in this camera shot, we're seeing 3 different stations. That's actually pretty cool. Good use of space, right? Gets the monitors up and out of there. All right, awesome.
He had a question. He wanted to know if he could measure or find the relationship between time and distance if he dropped something from a height. Okay, he wanted to see if he could record how far the thing went in a certain amount of time, but it was really difficult back then. He didn't have really nice fancy cameras and video equipment, so he said, what if I drop something, but I put something in the way? So it drops at a slower measurable rate, and what he did was he built a ramp, and he built a really fancy timing device too, whole nother story. And what he ended up finding out was something super duper cool. So what I've done is I've created this.
So there's a couple of really interesting things about this. So I love the ramp. It looks like it's a couple of really nice, sturdy ramps kind of tied together. That's pretty awesome. So it's nice and straight. Right away, I started thinking about the rolling features of this, right? I always struggle with trying to get students to realize, oh, the rolling, if it rolls without slipping, don't worry, everything's fine. That's tricky, right? Because usually when you're studying something like this, you'd rather have it be sliding, but then, you get friction, and that's always a pain. And what's so interesting is that the right amount of friction causes it to roll without slipping, which is the magic, which brings it back to being as though it's almost frictionless. It's actually really, really interesting how that works. Now, what I'm seeing on here are some markers. I see a blue one here, a red one here, and there's a black one, I think it was black, behind them. So I'm wondering if those are going to be used for timing. That's actually really cool. Can't tell what's down here, if it's going to smash into something when he lets it go all the way down. But I love how long this is, and I love the framing of the shot because you can see everything so well.
Ramp, and this ramp is at 5 degrees to the horizontal. Okay, so it's not a huge angle, but it's an angle.
So how would I double check 5 degrees? So I always think about angles that I can sort of see really well. So like 45 degrees. So 45 degrees is, here. And so 45 degrees would be, I'm just trying to think here, 9 of these? 1, 2, 3, 4. Huh. Boy. So if this is 5 degrees, we need 18 of them to get up to 90 degrees. I'm not sure that's 5 degrees. I need to think about that. I don't actually care. I don't think it's going to impact a whole lot of what's going on here, because if he's going after interesting relationships between how far it gets and how long it takes, it won't really matter. Well, if we assume all of these textbooks are the same thickness, I could measure it with pixels on the screen, but I don't think it matters. Here we go.
And you guys could probably guess that if something starts to go down the ramp, it's going to get faster and faster and faster. The whole idea of acceleration. So acceleration here in Denver is about 9.8, maybe just a tad bit less. Barely, maybe like 9.79563, something. Okay, give you an idea. We're going to use 9.8, okay?
Whoa, what just happened? Just go back for a second. I was doing some modeling recently. Oh, I was doing an oral exam and I was talking to a student about the Earth and there was some Earth problem or something. And I asked the student whether the thickness of the chalk that she used when drawing the Earth was was like bigger than Mount Everest. And of course it was, right? I mean, the Earth is huge. It really does look smooth. And so when you think about, oh gosh, we're up in Denver, gravity might be different. Gravity's not, I mean, not measurably different in Denver. What is different, of course, is the temperature to boil water. And so pressure, you don't really think about the air compared to, the air down at the center of the Earth. There is no air at the center of the Earth, right? So air pressure really does matter when you just get a mile higher. But wow, gravity probably doesn't. So I loved his joke about that and how, the book, the numbers that the students are going to be exposed to are going to work just fine even in Denver. Very cool.
Okay, you get the idea. We're going to use 9.8, okay? So,
That was awesome. So, I mean, I didn't even notice. 9.8, yeah, let's go. And so, hey, wait a second. It's not just a number. It has units. And did you see, go back, per second. Oh, that's so great, right? 9.8 meters per second every second. I love that. So rather than 9.8 meters per second squared, that was really, really cool.
I know how to figure out the component of this acceleration that's going to be acting down the ramp. It's actually pretty simple to do. It's another lesson for another class, but basically all I do is I take 9.8 times the sine of 5 degrees, okay? And I end up with about like 0.9 meters per second squared. Okay, so that's going to be my acceleration down the ramp. What Galileo found was something remarkable. He found that in 1 second, for example, in 1 second down a ramp, this ball, might travel this far. On this ramp, it's going to travel from here to here, okay?
Oh, that's what the markers are.
This much distance.
Awesome.
What he saw, though, was in the next second, it didn't travel this far. It traveled from here to here to here. It traveled, if this is 1d, 1 unit of distance, it traveled 3 units of distance. He's like, wow, that's pretty cool. What if I let it go for another second? Well, he did. So here, in this 1 second time period, it didn't go just 1d, it didn't go just 3d, it went 5d, 5 times this distance. And if I had a bigger ramp, I could show you that in the next second, it would go 7d, 9d, 11d, okay? You get the idea.
That's cool.
That's cool, but what does that really mean? Well, he thought about it, and he's like, okay, wait, from the very start, right here, from where this thing is going to begin, in 1 second it will go 1.
Yeah, so that's exactly what I started thinking about, right? I was expecting to get this quadratic effect, and when you add odd numbers, you get the perfect squares. So that's actually really, really cool. Anytime you get a particular thing happening in nature where only certain numbers are showing up, it really sort of gives you pause. It's just like the cicadas that are coming out, these brood X that are coming out on the East Coast, right? They have a 17-year gestational period, and that's not only is it an odd number, it's a prime number. And now that could just be coincidence, but it's not just coincidence, right? By being a prime number, it doesn't compete that much with the other broods that are other prime numbers. And so that's a way for nature to sort of evolve to this idea of, well, hang on, if I want these things to compete as in the least amount possible so that there's the smallest chance that 2 different broods come out in the same year, prime numbers is the way to do that. In the same way here that this way of measuring what is effectively a quadratic relationship is adding odd numbers. That is so cool.
1 unit of distance, or one measurement, okay, 1d. In 2 seconds, it's going to go from here, goes 1 plus 3, it goes 4d. In 3 seconds, it goes from here, 1, plus 3, now I'm at 4, plus 5 units of distance, that's 9.
Very
What
cool.
we found was that the distance the ball travels is proportional to the time squared.
Cool.
The distance it travels is proportional to the time squared. Do we have an equation that represents what Galileo discovered? The answer is yes. Delta x equals my initial velocity times time. I'm releasing it from 0. That goes away. Plus 1/2 a, well, that's the rate of acceleration down the ramp, times time squared, right? So delta x equals 1/2 a t squared. That is where that formula really comes from. Well, let's see if it works. I know Galileo could do it, and I'm not nearly as smart as that guy was. But let's see if we can get pretty close. Here we go. All right.
Oh. Boy, it settled down deeper than I thought it was going to. Maybe I don't fully understand what that thing's made of. Yeah. Huh. I thought that it would rest up a little bit higher. All right, let's watch.
3, 2, 1, 1001, 1002, 1003.
That was so cool.
That's pretty darn close.
That was so awesome. All of that was super awesome. First of all, the bangs and crashes when I got down to the bottom and the look on his face. But wow, that really worked well. And did you hear the little sounds that are, I'm guessing, post-processing? That was really, really interesting. And the markers are just big enough to really make the case. Wow, that was really, really cool.
May have broken something. We'll see.
Okay. All right, let me go back.
That's pretty darn close.
There we go. Wow. Okay, so first of all, the 5 degrees did matter, right? And I was thinking, looking at it again, maybe I'm not, let's see, so if I scooch up here and then scooch up another cinder block, that'd be 10 degrees, and another cinder block would be 15 degrees. Yeah, well, I'm definitely not even at 45 degrees. And then if I did another cinder block, yeah. Anyway, sorry, I should have just done a pixel measurement. So lots of really cool things in here. So when I think about some of the questions that he asked when he posted, say, hey, can you watch one of my videos? I thought this was great. I mean, I think at first I was thinking, oh, just roll it. I want to see. But honestly, I think that the expectation that he sort of set up, it was obviously done it before because the markers were in place. And of course, let me think here. The setup for this is interesting because he really wanted at least 3 seconds. 2 seconds wouldn't have been enough to be cool. So he knew how big the ramp needed to be. He knew what angle was going to make that possible. I do wonder how much trial and error was in here. And then once you get the ramp size, you get where you have to put the phone to get it to work. He asked something about the audio quality. I think that was great, especially the bangs and crashes at the end. I think the post-processing was cool, though not. The meters per second wasn't as necessary, though I think that if he's really harping on his students to do that, I think it was awesome that he took the time to fix it. I think that the little sounds, that was actually cool, though it did sound like he was saying 1001, 1002, in his own voice. Maybe a little clock somewhere, if there'd been just a ticking clock in the frame, that could have done the trick too. But I think this really got it down well. The only thing I wonder about is the value of, grabbing a whiteboard and writing the equation down rather than just saying it. Might have helped. This idea that adding odd numbers produces perfect squares, there's a really great, little graphical way of doing that by building, larger and larger squares, where you just have to add up the side and the roof. And then the little thing in the middle makes it an odd number. Might be worth it, but it kind of depends whether this is the intro piece to this, like, hey guys, now let's roll up our sleeves and do some cool work with it. What could you predict with this? You can actually predict quite a bit. It's basically saying, figure out how far something goes in 1 second, and you can figure out everything. Of course, not worrying about air resistance. I think that the rolling stuff that I talked about is not a big deal. That can be dealt with later. I don't know, there was so much I liked about this. So awesome. Well, hey, everybody, have a great day. And remember, physics teachers are awesome.